B, we're going to look at the second fundamental theorem of calculus, which allows us to connect derivatives and integrals in a much more elegant way based off of the first fundamental theorem of calculus. So let's take a look at what we're looking at here. So developing the second fundamental theorem of calculus, okay? So suppose we want to evaluate the definite integral of a function lowercase f that has a known antiderivative uppercase f over an interval a to x, where a is a constant and x is a variable, okay? So instead of having a constant upper bound, we have a variable upper bound x, okay? Here we replace x in the integral with t, so that way we don't confuse this variable t with the variable x we're using for the upper bound. So we're going to use t in this case right here for our integral variable, okay? So by fundamental theorem of calculus, okay, we know that the integral from a to x of lowercase f of t is going to be equal to changing its antiderivative f from between x equals a, or excuse me, between t equals a and t equals x. So we're going to have the antiderivative evaluated at x minus the antiderivative evaluated at a. Okay? So what we can take note of here is that if we take the derivative of both sides of this equation right here, okay, d over dx, all right, of the integral, that's going to give us a derivative of uppercase f of x minus the derivative of uppercase f of a. All right, so the thing to note here is that since f of a is a constant, okay, remember that when we evaluate the antiderivative at some x value or t value, whatever you want to call it, we're going to have a constant. So this last derivative right here is going to be 0. The first derivative on the right-hand side, however, uppercase f of x is a function since x is a variable. So right here we're taking the derivative of the antiderivative uppercase f of x. So as a result, we're going to end up with our original function f on the right-hand side as f is the derivative of, as lowercase f is the derivative of uppercase f. So as a result, we're going to end up with just lowercase f right here on the right-hand side. So second fundamental theorem of calculus will tell us that the derivative of a definite integral is going to be equal to the original function lowercase f, okay? So how is this quite useful for us? Okay? This result is known as the second fundamental theorem of calculus, and it states that differentiation, integration, or inverse operations undo each other. So essentially what that means is that if we take the derivative of an integral, we're going to end up with the original function inside of our integral, okay? The same way that in 4.5 a, when we took the integral of a derivative, we ended up with the antiderivative, okay? So differentiation and integration are inverse operations that undo each other, okay? So how is this useful? So let's say we're looking at the function e to negative x squared. E to negative x squared is known as a Gaussian function. It is famous as it cannot be integrated by hand. Thus, evaluating the derivative of the integral from 3 to x of e to negative t squared may seem overwhelmingly difficult. You're integrating a function that cannot be integrated and then differentiating it. But by the second fundamental theorem of calculus, the problem becomes quite simple. The derivative here is going to undo the integral to leave you with our original function. Okay? So the derivative of the integral from 3 to x of e to negative t squared is going to be nothing more than e to the negative x squared. We end up with our original function, but now that we've evaluated at x, we're going to replace the t with the x. So generalizing the second fundamental theorem of calculus, okay? So let's say now instead of having a lower bound a and upper bound variable x, we have lower and upper bounds our functions themselves, w of x and g of x, okay? So by fundamental theorem of calculus, okay, we know that this integral is going to be equal to the antiderivative evaluated at g of x minus the antiderivative evaluated at w of x. We replace a and b with w of x and g of x, okay? So as a result, when we take the derivative of both sides of this equation right here, we're going to end up with the derivative of f, uppercase f, of g minus the derivative of uppercase f of w, okay? However, because g itself is a function of f and w itself is a function of f, we must apply the chain rule for this specific scenario here for the right-hand side, okay? So this derivative right here is going to be the derivative on the right-hand side. The derivative of f with respect to g is going to be the derivative of f is going to be the derivative of f with respect to g times the derivative of g with respect to x. And then we're going to subtract that with the derivative of f with respect to w multiplied by the derivative of w with respect to x. We again apply the chain rule to f of g and to f of w. So as a result, this gives us a generalized result for our chain rule, or for second fundamental theorem of calculus. Specifically, when the integral has a lower and upper bound that are both functions, the derivative of our integral is going to be equal to the original function f evaluated g times the derivative of g minus the original function f evaluated w times the derivative of w. Okay? Again, the idea being is that the derivative of uppercase of f right here is nothing more than our original function lowercase f. So as a result, the derivative of uppercase f with respect to g and w is nothing going to be more than lowercase f evaluated at g and evaluated at w. Okay? This might seem esoteric, but the more practice we get with it, the better. And if at the end of the day you're really stuck on it, okay, we can focus more time on it. All right? For a time-saving measure, it's best that you memorize this equation and know it by heart, so that way you don't have to spend your time rederiving the second fundamental theorem of calculus over and over again. So let's take a look at example problem, okay? Evaluate the derivative of the integral of sine of t d of t evaluated from cosine of x to x squared, okay? So here f of t equals sine of t, while w of x, our lower bound function, is cosine of x, and g of x, our upper bound function, is x squared. So applying the generalized second fundamental theorem of calculus, we have as a result that the derivative of this integral is going to be equal to, applying the equation we developed on the last page, is going to be equal to our original function f evaluated g times the derivative g minus original function evaluated w times the derivative of w. So as a result, we know our original function is sine. We know that g is x squared, so we're going to have sine of x squared times the derivative of x squared, minus the sine of cosine of x, again w is cosine of x, multiplied by the derivative of cosine of x. So as a result, the derivative of x squared is going to be 2x, so we have 2x times sine of x squared, and then we're going to have minus negative sine of x times sine of cosine of x. Again, the derivative of cosine of x is negative sine of x. So as a result, our overall derivative of this integral is going to be 2x sine of x squared plus sine of x times sine of cosine of x. So this problem can be very esoteric and abstract in nature if you don't have this formula memorized, because it means you have to go through and derive a dozen and a half steps. But if you memorize the equation for a generalized second fundamental theorem of calculus, this equation right here, this problem becomes nothing more than plugging and chugging with basic derivatives. And this is the lesson for the second fundamental theorem of calculus.